Okay, Assalamualaikum and very good afternoon, everyone. Thank you for joining our session today. Um, I think we do have few announcements. The first one, your test one will happen in week 7. Unfortunately, we cannot conduct the test during lecture period. Yeah, I would like to suggest lecture will run as usual on Tuesday, the on Tuesday the 10th, and your test, my suggestion is to conduct the test on the same week, but at night, on Thursday, the 10th, the 12th, the 12th of yes, correct, the 12th of May. Yeah, so I will write the notes here. Yeah? Lecture will be as usual on end of May. Um, May. There's one. There's one. Yeah. There's one. 5th of May at 8 p.m. We start at 8 p.m. till 10:30 p.m. Is there any problem at night? Anyone having a replacement class or you have a lecture at night? Ada ke anyone having any problem? Hospital appointment?
I think no, doctor, because like everyone is free during that time, maybe.
Okay, all right.
Yes.
All right, so that I think it would be better to conduct the test few days after a long holiday so that you will have ample time to study. Still an online test, but online test, open book test, but no discussion is allowed, So for that reason, we shall conduct the lecture as usual on the 10th of May, and test will be on the 12th of May. Do let me know if anyone, especially for those who have a hospital appointment. Yeah, let's say you have hospital appointment on 12th of May, so that we shall conduct your. You have hospital appointment on the 12th, so test will be on the 13th. Yeah, so let me know. All right. Let me share my slide. Announcement is I have another announcement. After week 8, maybe we are going to have one or two face-to-face lecture session, but I'm thinking of bringing all of you to a site for a site visit, to a wastewater treatment plant. That depend on the clearance from the water or wastewater operator. It's not me to decide whether we will be allowed to visit or not, but I will try to discuss with my former student, for my master student, my former master student, if we are allowed to do a visit, maybe somewhere in week 10. That is another reason I cannot conduct the test during lecture hour, because there will be 1 week where I will try to arrange for a site visit, and I will and definitely we will arrange the visit during our lecture time, during lecture hour, so that no one will be affected. Maybe it will happen around week 10. I will update you in case that we are not allowed to arrange for a visit. I will replace the session with the visit around UPM. Maybe we can, I will arrange the visit to our lab. I think you are the batch with the online lab kan. So maybe some of you, it would be great to visit the lab. I will show you the bioreactors for the treatment, but that will only happen if we are not allowed to do a site visit. Okay, because this semester is considered as a hybrid session. So I will try to arrange a face-to-face session, but will replace with a site visit. If we are not allowed to do a site visit, then we shall replace with a lab visit. Okay, at least you will have experience having a lab tours, not exactly a tours. Yeah, you will be able to demonstrate, few to using few equipments. Yeah, so at least you have the hands-on experience. Yeah, because you are the best with online lab session. Yeah, okay, thank you. Okay, that's all. Right, I would like to continue my lecture today. Let me share the slide first. So please make your time, yeah, during week 10, yeah. We shall arrange for the visit. Yeah. Hope will be granted. Right. Okay. So our lecture today is on the topics of wastewater treatment plant. It's a conventional system integrated with membrane bioreactor. Okay. All right. I do notice that this is a part, yeah, of the syllabus which we have discussed before during your third year. Yeah. But during your third year, uh, we did not integrate, we have never integrate the membrane bioreactors, into the design of activated sludge system. So the first few slide will be only the revision. I consider it as a revision because already covered, already discussed during your third year. It's a part of water and wastewater treatment process. And the final section will be on the membrane bioreactor. So this is the part, this is the updated part, for this course. Yeah? All right. All right. Oh dear. Um, looks like I have to. Okay. Okay, next, so these are the design parameters. We do have the characteristic of the wastewater in table 5. The characteristic of the wastewater presented in table 4, as well as the operational parameters in table 5. So operational parameters in table 5 is actually the target quality of the treated wastewater. For example, effluent BOD, the system that we are going to design has to comply with the targeted BOD, which should be less than 30 milligram per liter. Same goes to the TSS and others parameters. Okay, so the yield, mean cell resident times is the slash age, the theta C. MLVSS is the mixed liquid volatile suspended solid, VSS. So VSS is important to represent the population of microorganism. All right. BOD, you are given in the middle column, you are given the BOD5 over BOD ultimate is equal to 0.75. These are the recommended ratio. And the ratio of VSS over SS is 0.8. So this ratio is important because we would like to calculate the amount of waste sludge later. Okay, so bear in mind, whenever we are to design an activated sludge system, definitely we will be having a screening process, a primary process, a secondary process. So in this case, during the screening process, it is assumed that 15%, yeah, of the BOD as well as 25% of the TSS has been removed, yeah, during screening process. Yeah. The following process is BOD and TSS, which is in the equalization tank. Yeah. This is a primary process. So in this process, it is expected that BOD to be removed around 30% and TSS about 55%. Okay, so we need to consider this because it is almost impossible to run a secondary system or a biological system without a pre-treatment. And therefore, BOD, some of the BOD as well as TSS should has been removed before the influent can reach the secondary tank. Okay, so on my right side is the table 4, which is the raw wastewater characteristic. The BOD is around 1,300. COD is just double the BOD. TSS is about 700, and the design flow is about 52 meter cube per day. All right. The preliminary treatment, during prelim treatment, yeah, for example, like screening process, yeah. So some of the BOD has been removed, yeah. So first, you need to calculate the BOD loading. Yeah, this is very easy. You are given the concentration of the BOD previously, yeah, n times you have to multiply with the average flow. Then you will get the BOD loading in kg per day. Same process to happen whenever you calculate for the TSS loading. Yeah, I'm going to go through this very fast, yeah, because this is only a revision. Okay, then you can calculate the TSS loading, which is about 36.6 kg. Same step, the given concentration of the TSS times with the Q average. Q average is given here, yeah, table 4. Then you calculate for the BOD removal. Yeah? How to calculate BOD removal? BOD loading, which you have calculated earlier, 67 kg per day, times with the percentage of the BOD removed. How do we know this? It is actually assumed. Yeah? This is an assumption that 15% of the BOD has been removed during prelim stages. Yeah? So that the BOD which has been removed is about 10 kg per day. The same step for the TSS removal. Okay, for TSS removal, don't forget to change the percentage, yeah, because the percentage of the TSS which is expected to be removed during prelim process, which is screening is a part of the preliminary process, is about 25%. Yeah. All right, next in equalization tank, which is the primary process. In this process, we have to moderate or normalize the flow rate based on the cycle. Yeah, based on the cycle. Since we are designing a wastewater treatment plant, yeah, for a wet market, this is a wastewater treatment plant for a wet market. So, this wet market is only operated for 18 hours. Yeah, it's not like a conventional wastewater treatment system. It's working for 24 hours, kan? But in this case, if 24 hours, then you are going to have the same average flow rate lah. In this case, we have to normalize because the operating period is only 18 hours. So these are the actual average hourly flow rate. Yeah. Then since the MBR, the membrane bioreactor the membrane bioreactor treatment operation take 12 hours. Yeah. So 12 hours. So the average hourly flow rate times the 12 hours. So you will get the volume of the water, the wastewater to be treated. Yeah. From the volume of the wastewater to be treated, then you can calculate the sizing for the equalization tank. Yeah. Okay, the sizing for the equalization tank, yeah, take the depth is equal to 3 meters, the freeboard is equal to 0.6 meters. So volume is equal to length times width times depth. So given to you that the ratio is the length to the width is 3 to 1. Yeah, so the L is equal to 3W times W times 3. 3 is given here. The depth is equal to 3 meter. So the volume you have calculated earlier. So you should be able to get W and L. Yeah, and don't forget to consider the freeboard. Yeah, you have to add letter. Yeah, because freeboard is not a part of the actual depth. That is the excess. Yeah, the extra depth of the tank. Okay, next you calculate the remaining BOD and TSS from screening. Okay, this is correct and not BOD remove. This is BOD remaining. So how to calculate BOD remaining? We have to consider the actual this is the actual BOD load, and these are the BOD which has been removed during primary process. Yeah, during preliminary process. Yeah, this is the BOD which is removed during during screening process. This is the amount of TSS which has been removed during screening process, so that you have to the actual BOD, yeah, the actual BOD load minus the BOD which has been removed during primary process. Same goes for the TSS, and now you have the BOD remaining and TSS remaining. So these are the BOD as well as the TSS which is to be treated in the secondary tank. Okay. Sorry. These are the BOD and TSS which are to be treated in the primary tank. Okay, because this one 10.31 is obtained from the preliminary can. Okay, next BOD removal. BOD remove is equal to 58.41 kg per day. Yeah, this is the remaining times 30%. 30% is the expected BOD to be removed during primary process, which is in this case is equalization tank. So then you will get the BOD removed. BOD remaining is equal to BOD loading minus BOD remove. Okay, how to get BOD load? How to get the BOD loading? And BOD loading is the actual load that you have calculated um, earlier. Sorry, BOD loading is the remaining BOD. So in this case, 58.41. Can someone check for this? 58.41 minus 17. I think the answer is 40. Can someone check? Calculator. 58.41 minus 17.53. Oh dear. Minus 17. Yes, correct. Yeah. So how to get BOD remaining? 58.41 here minus 17.53. Okay, so that you will get BOD remaining. Yeah. These are the BOD which is to be treated during the secondary treatment. Why? Because we have calculated earlier, these are the amount of BOD to be removed during primary process. So the BOD loading minus BOD remove, BOD loading, which is the BOD remaining from the preliminary process minus the BOD removed during primary process, and you will get BOD remaining to be treated in secondary tank. The same steps are going to happen for the TSS. Then you can also you can also calculate for the sludge flow rate. Sludge flow rate, normally the value is extremely small, but you can consider, sludge flow rate is equal to TSS removed over specific gravity of the particles. Normally we use specific gravity of the sand, which is 2.65 times 1000, which is the density of water times solid content. Solid content is given earlier, so that you will get SFR is equal to 0.13 meter per day. Okay, these are the calculation for the secondary tank. Okay, the calculation for the secondary tank, you have to consider the Q in the actual Q in. That's why we calculate the sludge flow rate just now. Knowing the slash flow rate, you will get the Q in, the actual Q in, but we only consider 50%. Yeah, 50% of the wastewater to flow because it's operating for 2 cycle. Yeah, the system is operated for 2 cycle, so you only take half of the flow rate. Okay, then you calculate for the BOD in. BOD in is also the BOD in is also known as S-note, the same thing. Yeah, the original BOD. Yeah. Then you can calculate for the TSS in. So these are the BOD and TSS which are to be treated in the secondary tank. Okay. Then you can calculate for the soluble BOD which will enter the hollow fiber membrane. To estimate, to determine the BOD5 of the effluent suspended solid, assuming 85% biodegradable solid and 1.45 milligram of oxygen is consumed. Yeah? This tells us that for each gram, yeah, of the cell which oxidize the waste, it will take about 1.45, yeah, milligram of oxygen. Okay, so effluent, the BOD, this is the target effluent given earlier, time 85%. So you will get biodegradable effluent solid about 25 milligram per liter. Then calculate for the BOD ultimate by using 1.45 milligram of the oxygen just now. Okay, you can calculate both, yeah, for the BOD as well as the COD, but we shall only use the value of the BOD throughout the calculation because most of the waste consists of organic matter. So BOD is more popular to be used for the design of a wet market system, of a wet market wastewater treatment system. Then you can calculate for the effluent BOD, which is equal to influent BOD plus BOD of effluent. So 30 milligram per liter is the target effluent just now, equal to S, yeah, plus 24.8, 24.8 is from here, so you will get the value of S. Yeah? Then you can check for the treatment efficiency. Okay, after you have checked the treatment efficiency, then you can calculate for the dimension of the aeration tank. Yeah. So again, this one, for this tank, we shall use the depth of the 3 meter. If it is not given, then you can assume. Yeah. Then, but since the flow rate is very low, the value must be accepted. So normally we have to consider about the freeboard of 0.6 meters too. So knowing the volume, yeah, the volume is about 26.09. Where do I get the volume from here? 26 point. Yeah, they use the flow rate because it's per day. Yeah, so 26.09. Solve for this equation, the length to width ratio is given here as 2 to 1. Yeah, previously we used 3 to 1 can. So now you can get W and N. So consider also the free point. Yeah. Okay, up to this point, do you have any question? Okay, good question. Yeah. Okay, then you can calculate for the oxygen requirement. Okay, oxygen requirement is no longer part of your syllabus lah. Yeah, your syllabus only up to this point. Oxygen requirement is have been calculated in the third year subject. Yeah, in the third year subject. So just to let you know, yeah, that your syllabus is only up to this point because only up to this point is required for further calculation to design for membrane bioreactor. Okay, but since is in a one note, one set of note, so I will go through very quickly this section how to calculate the oxygen requirement. Okay, in the previous slide, you are given that the BODS is equal to 5.22 milligram per liter. So you can calculate the BOD ultimate use. Yeah, BOD ultimate is equal to Q in S note calculated earlier. As 5.22 also you have calculated earlier. 5.22. Where do I get the S note? S note from here. Okay. So then you solve for this equation, you will get the BOD ultimate. Okay, then we have to calculate for Y absolute. Y absolute is important. Yeah? We have to calculate this because Y absolute will tell us about the waste activated sludge. Yeah. Okay, so Y absolute is equal to 0.5 over 1 plus um, 1 plus 0.006 per day. This is actually the equation. Yeah, this is actually the equation. So 1 plus KD, 0.006 per day is the KD. Yeah, KD is given earlier. Here, the decay constant. Okay. Then delta C, the slash age, 5 days is also given. But this is a mistake. Yeah, it is actually 0.06, not 0.006. Yeah, but the answer here is correct. Okay, once you have calculated for the Y absolute, then you can calculate for the PX. Okay, PX is important because later we need to calculate for the PY. Yeah, what is PX? Yeah, I have an extra note here. PX is equal to mass in mlVSS and PY is the mass of the mlSS. Yeah? So given earlier that the ratio of VSS over L over SS is equal to 0.8. Yeah? So that you calculate for the PX, you solve for this equation, and these are the equation to be used. Then you can calculate for the oxygen requirement. Okay, the oxygen requirement. Okay. Then calculate for the sludge wasting. Sludge wasting, okay. Sludge H is given as theta C is given in the earlier section as 5 days. You need to find the value of QSW. Okay. The QSW, this equation, if you notice here, 50 milligram per liter times 0.8, where do I get this value? 50 milligram per liter is from the TSS concentration given in the earlier section of the slide times 0.8. Where do I get 0.8? 0.8 is from the ratio which is given in the earlier section. This one, yeah, 0.8. So that you, because we would like, we want to know the mlVSS. Yeah, XE is actually the mlVSS. Yeah, so that uh, to get the mlVSS, we need is this is actually equal to mlSS times 0.8. So mlSS is given as 50 milligram per liter times 0.8. Okay, you solve for this equation, then you get the QW. Okay, step 2 is to calculate for the PY. Okay, PY is actually the increase of the mass. Yeah, increase of the mass of mlSS. So since we have calculated earlier the PX. Yeah, so again I put extra note here. PX is equal to mass and in mlVSS. PY is the mass in SS. Okay, so that definitely PX over PY equal to 0.8 lah. Yeah, so PX over PY equal to 0.8. Since you have calculated earlier the PX, so you should be able to get the PY. Okay, then you can calculate for the TSS loss in the effluent. You can see the TSS loss in the effluent is very small, only 1 kg per day as compared to the flow rate, to the treated water. So normally we have to check this because it will tell us the indication of the quality of the treated effluent. If you can have a look here, we consider the total Q in, minus the QSW. Yeah, so these are the importance of calculating the QSW. Yeah, uh, this is the sludge wasting flow rate. Yeah, because Q in is the actual flow. Yeah, minus the sludge wasting flow rate, then times with the concentration, the target concentration of the total suspended solid. Yeah, so that you will get the the TS. Okay. So you will get the PL, which is the TSS loss in the effluent. Meaning to say that this will be the concentration of your TSS in the treated wastewater. Okay, the final section is on the membrane bioreactors facilities. Okay, these are a ready-made membrane system. Yeah, we are not yet in the topics of membrane, but this is a small introduction lah. Yeah, a simple introduction on complete membrane system. You can see the design flow is between 10 to 20 liter hour meter squared. These are the recommended flow and these are the filtered area. Okay, the pore size is about zero point 0.1 micrometer. The porosity less than 80%. Okay, so considering these are the spec, yeah, of the membrane. In this case, they use the hollow fiber membrane. Remember, I did mention to you 3 weeks ago, there are many types of membrane. Yeah, they are classified based on the pore size. Yeah, so the hollow fiber membrane, whether they are hollow fiber membrane, whether they are flat sheet, whether they are tubular membrane, these are only the configuration, cara mereka menyusun membrane tersebut. Ya, but the membrane are being classified based on their pore size. Ya, for this reason, nanofiltration can also exist as a hollow fiber. Ultrafiltration can also exist as a hollow fiber. Microfiltration can also exist as hollow fiber membrane, because different pore size also can be arranged based on the types of the membrane. Yeah, so we do have hollow fiber, flat sheet, as well as tubular membrane. These are the most popular configuration and membrane configuration. Okay, then compute the daily permit flow per cycle, QP equal to 20 liter hour meter squared, the spec of the membrane itself. So this for membrane is going to be operated 12 hours. Yeah, there are 2 cycles. So you calculate for the 12 hours times 25, the standard filter area, and times 5 cassette. Okay, 5 cassette is based on how many numbers of the hollow fiber membrane that we would like to use. Yeah, sometimes if we employ recirculation, maybe we can reduce the numbers of the hollow fiber cassette to be used. Yeah? So in this case, they suggest 5. So it tells us that the daily permit, yeah, what is permit? Yeah, permit is the treated wastewater. Yeah, the treated water after is already passed through the membrane. So in this case, uh, in this system, it will produce about 30 meter cube, per cycle. Yeah, the product water, the treated water or treated wastewater. So for that reason, since there will be 30 meter cube per every cycle, so per day there will be 2 cycle. Yeah, what is actually 2 cycle? 2 cycle meaning to say that there will be 2 times of flushing of the wastewater onto the membrane system, into the membrane system. Yeah, 2 times, twice. Yeah, the wastewater will be flushing into the membrane system twice per day. This is what I mean by cycle. So in this case, there will be 2 cycle. So that's why for we have to we need to calculate for daily. Daily. So since every 12 hours, wastewater will be flushed on into the membrane system, so it will happen twice. So if twice, then the total QP average is about 60 meter cube per day. So basically about 60 meter cube per day of the product water or the product wastewater will be produced from this system. Okay. Alright, please do let me know if you have any question regarding on this slide. This is a design question. So you have to understand a few steps, especially on how to calculate the BOD remaining, TSS remaining. On oxygen requirement, is no longer a part of your syllabus because it has been covered during the 3rd year of study. But you can go through as a revision purposes. But just to be honest with you, it will not be come out again in your test or final exam. This one, oxygen requirement, as well as the slide number 8 as well as slide number 9 will not be come out again in your test or final exam, because it's no longer as a your syllabus. So the rest of the slide still is covered as a part of the syllabus in this course. Yeah. All right. Next slide is on notification, denotification. No, the sequencing a batch reactor. Alright, before we can we can start with the sequencing of batch reactor. Yeah. Today we are going to cover about four system: sequencing a batch reactor, trickling filters, RBC, and moving back bioreactor. Okay. Alright, there are two types. Just to recap, yeah, uh, we are exploring the aerobic system, which there are two types, which is attached growth system or biofilm, and also the second one is suspended growth. Yeah, attached growth, the rules is very easy. As long as you do have the filter media, as long as you do have the support carrier for the microbes to grow, so that is known as the attached growth system. Yeah, but if you employ a tank or you employ a pond without any support media, yeah, only the sludge into a tank, then it is known as suspended pond, as suspended growth. Yeah. So today we have covered up to activated sludge process. Now I'm going to complete the sequencing batch reactor. Then we shall explore on the attached growth system. Okay. Before we go further, yeah, you can. Oh dear. Looks like I have to reopen the slide again. Yeah. This one is 4 point. Alright. Before we go further, yeah, I would like to have a very short description on sequencing a batch reactor that will be followed by the video. Yeah. So sequencing a batch reactor is a system where we only need two tank to complete the entire process. So in other words, sequencing a batch reactor has been designed as an improved version for the activated sludge system. Yeah, activated sludge system is a system where it require, yeah, larger area. Yeah, because we need a primary system, we need uh, the we need aeration tank, clarifier, sludge treatment. Yeah, so by employing sequencing a batch reactor, we can minimize the area required, as well as it will minimize the sludge production. Yeah, so by employing this system too, it can help to improve or to remove the nitrogen as well as phosphorus content. Yeah, by employing this technique. So it comprises of the, definitely whenever we have a wastewater treatment system, we need a screening process. That is a physical process to remove the larger debris. Yeah, so it will followed by the equalization tank. The function of the equalization tank, yeah, is to control the volume of water into the major tank. Yeah, so in this tank there will be four processes, yeah, will occur. The first one is known as filling. The second one is the aeration. Filling is the process water, wastewater being added, yeah, into that tank. Then this will take about 6 hours. Not exactly 6 hours. Yeah. The correct statement is it will take about 25% of the actual process. For example, if the flow rate is fairly low, so that the operation will be only 18 hours. So the 18 divided by 4 lah, or 25% out of the 18 hours. Yeah. So let's say this is 24 hours operation. So spinning will be 6 hours, aeration 6 hours, settle 6 hours, draw off for 6 hours. Okay. So this is how does it happen. Everything will occur within the same tank. Yeah, within the same tank. So in this process, both aerobic and anaerobic process will occur. You know why? Because during the aeration, oxygen will be supplied. Then there will be 6 hours without any oxygen be supplied. Yeah. So filling react. Yeah, react is after air being added. Yeah, after oxygen being added, then we will allow some settlement. Why there will be settlement? Yeah? Because when we supply oxygen into the tank, microbes will utilize the oxygen to biodegrade the waste. So the product of this biodegradation process is a suspended solid. Yeah, it will produce some biomass. So this biomass is going to settle to the bottom part of the tank as sludge. Yeah, so it will take 6 hours for each of the processes. Okay, let's watch a video. Okay, there is no voice for this video, but you can always read. Okay, these are the entire process. Yeah, the entire process. It will start with the screening process, and these are the equalization tank. Yeah, these are the major, and the following one is the major tank. In this tank, In the sequential batch reactor tank, these are the tank where there will be at least 4 processes will occur consequently. Yeah. So after this process, it will produce sludge. Yeah, it will be going for the sludge treatment as well as the treated water. In some cases, the filtrate, there will be some of recirculation of the sludge of the biomass into the sequential batch reactor system. Okay, that's one. Okay, next, okay, these are the advantages lah, of having this system. This system is basically a simple process. Fill, react, settle, and draw. Yeah, it comprises of equalization, biological treatment, and clarification is achieved. All these processes can be achieved within a single reactor. Yeah, we can have a better aeration control. We can treat or remove nitrogen. Yeah, denatrification, the nitrogen removal, and lower power consumption too. Yeah, so denatrification is the process that occurs in any water bodies for the nitrogen removal. After the semester break, we will be going through these topics on denitrification as well as nitrification process. Biological nitrogen and phosphorus removal without need for the chemical. So these systems are good for the N and P removal. It's simple in terms of operation, and minimal the footprints. These are the major advantages as compared to the conventional activated sludge system. So for the design parameters for the SBR is required minimum 2 units. Two units. The depth is about 3 to 5 meters. The freeboard is about 0.5 meters, and the foot to mass ratio is the waste to the microbes ratio is about 0.05 to 0.1. There are two types of SPR. The first one is continuous fill and intermittent decant. Another one is intermittently fill and intermittently decant. So normally the second column are more popular. The one that we visited that I have visited before 5 years ago at Ceras, they employ the second column system. So the HRT in total is about 18 to 24 hours. Depends on the flow rate. But last time when I visited the wastewater treatment plant in Banatul Razak Ceras, their system is about 24 hours. So 6 hours for the, let's say we do have 4 major processes, so 6 hours for filling, 6 hours for reacting, 6 hours for settling, and 6 hours for draw. So these are the beauty of having SBR system. Okay. So these are the guidelines from the SPAN, more or less as presented in the previous table. There is, there is extra information here regarding on the BOD as well as dissolved oxygen and also organic loading rate. For the BOD, it has to be minimum 2 kg of oxygen per every kg substrates to be removed. The dissolved oxygen has to be minimum of 2 milligram per liter, and the loading rate is about 0.1 to 0.4 kg BOD per meter cube day. By the end of this slide, I will have an example on how to calculate the OLR. Okay. Next, we continue with the RBC. This is rotating biological contactors. Maybe we can go for the calculation of OLR first. Um, Okay, what is OLR? By definition, OLR is the organic loading rate. Is the weight of the waste given to the weight of the waste given to certain volume, of the tank or of the reactor. Okay. Um, Okay, so the organic loading is the amount of COD or BOD applied, to the filter or reactor per volume of filter media or reactor per day. Yeah, so the unit is expressed is as BOD gram and not gram per liter. It has to be gram. The weight of the BOD, the weight of the COD per meter cube. Meter cube here is the size of the reactor, the volume of the reactor. Yeah, and per day. Okay, so example 2, calculate the organic loading rate of 0.6 meter cube filter with an influent BOD of 1200. 0.6 meter cube is the volume of the bioreactor or the tank or the filter. Then the BOD concentration is 1200, HRT is 0.5, and the volume of the incoming flow is 400 liters. Yeah. Okay, then first find the gram of the BOD. How to find the gram of the BOD? Very easy. Concentration times the volume, so that you can cancel out the liters. So you will get the BOD in gram. Volume of the filter or the reactor is 0.6 and the HRT is given as 0.5. And you solve for this equation, you will get 1600 gram of BOD per meter cube. Meaning to say that every meter cube of the reactor, you give them about 1600 gram of the BOD. Okay, so this how do we define the organic loading rate. Okay. Okay, let's go for a very short introduction on the rotating biological contactors. Yeah, in the previous year, you have studied on the theoretical of the RBC. Yeah, but you did not you did not conduct any design calculation. You did calculate for the area required, but there is no detailed calculation on the stages as well as the train, for the RBC. Okay, so very short description on the RBC is a fixed film biological secondary treatment device. So the concept of RBC, we have a rotating drum with a filter media so that microbes can stay within the media, so it will rotate. Yeah, so it will rotate to get intact with the wastewater. Okay, so let's watch this. This is a very short video. What is RBC? Sorry. Why is still on? One second, let me copy the. Okay. They're getting excited knowing that we are coming. They're running here. You look at that. Okay, so these are the RBC, rotating biological contactors. Yeah? Okay, these are the drum. Within this media, they are microbes. They are microorganisms which has been cultured. So at the bottom part of the system, these are the wastewater to be treated. Okay, very short video. These are the wastewater to be treated. So the RBC will be rotating. Yeah, the RBC will rotate, so that it can get intact with the wastewater and so that can treat the wastewater. Where is actually the microbes? Microbe is here. It's staying within the filter media. So the concept of RBC, the filter media will rotate so that it can get intact with the wastewater at the bottom part of the tank. Okay, So this system again is an aerobic system because it's an open system where we allow the oxygen to get intact with the microorganism. Yeah, this is still an aerobic system. Okay, so let's continue. Okay. Okay, normally when we employ RBC, yeah, the shaft continually rotates at 1 to 2 RPM. Yeah, very slow, and a layer of biological growth to 2 4 mm thick is soon established. Okay, once you keep rotating the arm just now, the drum just now, it will get intact. The microbes will get intact within the filter media, continuously biodegrade the waste, and after certain period it will develop a layer of slime, yeah, on the filter media. And this slime are extremely important because when the slime exists, it indicates the process occur. It shows the performance of the process. So that after certain period, the slime will get thickened, so that it will be removed from the filter media. Yeah, sometimes it's require uh, manual cleaning. Yeah, but the slime is very important. It has to be exist, otherwise no biological process occurs. Yeah, later I will share with you how the colors of the slime tell us the process performance of the system. So these are the schematic diagram on the RBC. Basically, we still need the primary tank, but there will be series of the drum here, and these are the secondary tank. Yeah, so typically a single contactor is not sufficient. Yeah, typically a single contactor definitely is not sufficient. We will need at least three stages or three strain to complete the entire process, because this is where that we keep recycling the. My son is also doing his reading. Okay, all right. Typically is require series of drum, yeah, so that the wastewater can get a better impact with the microorganism. Okay, so each individual contactors is called a stage, and the group is known as a train. Later, when we do the calculation, yeah, I will share with you what is the train, yeah, what is the stage, yeah. So most of the RDC consists of two or more trains and at least three or more stages. Yes, at least there will be two in a row or two in a column. But in most of the time in the design, we put three in a row and three in a column. Yeah. So this is what does it mean by stages and also train. Okay, so this is what I meant just now. Different colors, yeah, of the slime indicates different process performance, yeah, of the RBC. Yeah, let's say if you have a gray, shaggy slime growth, that indicates a normal operation. Yeah, nevertheless, yeah, if you collected if you can see the reddish brown, golden shaggy growth of the slime, so that indicates heavy, serious problem of nitrification, which indicates that higher nitrogen content in the wastewater being treated, or then less, or we have to supply more oxygen in this case. When we have high concentration of nitrogen in the treated in the wastewater to be treated, or in raw wastewater, sometimes we have to supply more oxygen. Yeah, because to treat carbonaceous, BOD is required only one group of oxygen. But to treat nitrogenous BOD is required four times, of the oxygen. So let's say if the reddish brown or golden shaggy growth, that indicates of higher nitrification process, higher nitrogen content. So it tells us that the system, the oxygen is not sufficient for the microbes to biodegrade the waste. The oxygen is not sufficient, yeah, due to high concentration of nitrogen in your wastewater. Yeah. Next, white chalky appearance, high sulfur. Yeah. And no slime, severe temperature or pH changes. Yeah. When there is no slime being developed, this indicates there is no biological process. Yeah. The process is not completed. Yeah. Is incompleted. Yeah. So definitely there is something extreme which has happened. Yeah. For example, extreme change in the organic loading rate, yeah, extreme change in the pH of the wastewater. Okay, for example, today you feed the system with domestic wastewater. On the following day, you feed the system with the food and beverage industry wastewater. Yeah, definitely they will get shocked. Yeah, that's why there will be no slime produced in the system. Yeah, this is due to the extreme condition. It's very difficult to find this scenario when no slime will occur, but it can. Yeah, there is possibilities. Okay. Next one is on RBC. The why this system are covered. Okay, RBC are to be covered due to 3 to 4 reasons. The first reason is not happen in this country. Because we need to protect the RBC, protect biological slime growth. From the freezing. Second, we have to protect the RBC unit, the drum just now, from the heavy rain. Third, to protect from the direct sunlight, because direct sunlight can cause the growth of the algae. Yeah. Next one, to avoid exposure to the media to sunlight, because the media itself can turn into can become brittle, jadi keras. So that's why we would like to avoid from direct sunlight and to provide a protection, for the operators. So that's why it's better in the RBC units are covered lah. Okay. Next, in regard to this typical performance, so normally when we employ RBC, we can remove the BOD up to 80 to 95%, as well as the solid at 85 to 95% too. So this process are also good for the removal of organic nitrogen as well as ammonia nitrogen. If we talk about the sequencing a batch reactor just now that we studied earlier, so it's good for the removal of nitrogen and phosphorus. While for the RBC is good for the nitrogen as well as ammonia nitrogen. Okay, phosphorus. Most of the system, not so many biological system can remove phosphorus effectively, unless you combine. You combine the anoxic condition, the oxic condition, the anaerobic condition. If you employ this simple only one condition treatment methods like this, which is aerobic, so it's not easy to simply remove the phosphorus. So that's why in some cases chemicals will be added. What we studied before, they add what? They add the ferric chloride, for the removal of phosphorus. Okay. Then advantages, that offered by the RBC. The first one is short contact period. RBC are capable of handling a wide range of flows, and slough biomass generally has a good settling characteristic. Yeah. And operating costs are fairly low, because little skills required, short retention time, low power requirement, and low sludge production. So these are the major advantages now, as compared to the conventional activity sludge system. The disadvantages of the RBC is requirement for covering the RBC unit in northern climates to avoid the freezing, and shaft bearing and mechanical drive, because it's required rotating gun. So that's why we have to monitor to avoid any mechanical problems. So it's require frequent maintenance. Okay, next. is on trickling filters. Okay, what is the difference, yeah, between RBC and the trickling filters? Yeah, both of them, yeah, both of this system are attached growth system, where the spirit of employing this system is having a filter media. Microbes will stay within the filter media. But the major difference between these two processes, between the RBC as well as trickling filters, are in the RBC, the rotating arm will rotate, yeah, so that it can get intact with the wastewater, which is at the bottom part of the system. However, in trickling filters, there will be a rotating arm. Yeah, rotating arm is the one which is keep moving so that it will splash the wastewater onto the filter media. So in this case, the wastewater is moving onto the filter media. Okay, so employing this system, normally trickling filters, we only use one set of system. It's not like RBC just now. There will be there will be series of train and series of stages. But for trickling filters, only one set of system. For this reason, yeah, for this reason, in a trickling filter system, normally we have to employ recirculation. The wastewater which has passed through the filter media will come back. Yeah, will be recirculated for a better removal rate. Okay, these are the real photos of trickling filter media. How does it look like? Yeah, so they are form of, most of them are plastic, some of them are polymers, but most are plastic. Yeah. So the trickling filters consist of the major components including the spray head, the media. Yeah. So in the influent, the system more simple as compared to the RBC, but to get a better removal rate, you have to employ recirculation, meaning to say that the effluent produced at the bottom part of the system after passing through the media will be recycled again as the influent. Because if only one run, then you cannot achieve the target effluent concentration. Okay, because it was too short. Yeah, the period with the filter media, the contact time, yeah, between the microbes as well as the wastewater is too short. Yeah, that's why it cannot meet with the effluent requirement lah. Yeah, so the organism aerobically decompose the solid, producing more organism and stable. So again, in this system, it will also produce the layer of slime lah, layer of slime. So we can monitor the performance, yeah, by having the layer, by monitoring the color of the slime. On top of that, yeah, employing the trickling filters also require some air flows. Yeah, you have to supply extra air from the bottom to the top or top to the bottom, depending on the temperature. Yeah, so otherwise, if we only depends on the natural aeration, yeah, natural aeration, sometimes it's not sufficient. Yeah, the oxygen is not sufficient for for microbes to do their work. So it end up, this system is more risky as compared to RBC. Sometimes it can end up having the problem of bad odors. Yeah. Oxygen is transferred, yeah, from the air to the wastewater and slime to maintain the aerobic condition. Okay, so uh, likewise the RBC, here we have to periodically remove the slime. Okay, trickling filters may be classified into two types. The first one is low rate, the second one is high rate. Yeah. So for high rate trickling filters, they will employ recirculation. Yeah. So as I mentioned just now, it's required, yeah, to employ recirculation, because by recirculating the waste, we can dilute the strong waste, which can improve the removal efficiency. Okay, the process design. For the process design, for the trickling filters, yeah, the BOD recommended for low rate is 0.11 to 0.35. The high rate is about 0.37 to 1.85. The depth for the low rate without recirculation. But when we mention a low rate, it is a system without recirculation. So you can see the depth is about 1.8 to 3.0. So the depth of the filter media, in other words, for the system without recirculation, is normally deeper. Yeah. While with the system with recirculation, the depth is around 0.1 to 2.4 only. Yeah. So the problem, yeah, with the system is many flies uh, and chances of odor. But when you employ higher rate filter with the recirculation, so this problem can be reduced lah, it can be improved lah in terms of the problem of less odors and the flies. Yeah. So if you supply less oxygen, yeah, if they don't receive sufficient oxygen, microbes will die. Yeah, so that is the reason why it will produce, it will smell very badly. Yeah, the system will smell very badly because no biological reaction occurs. Yeah. Okay, so these are the diagram for a low rate system, low rate TF. PST mean primary settling tank. It will flow into treating filters and secondary settling tank. That's it. Only in one run. Comparing to the high rate with a recirculation, so you can see, yeah, from the secondary tank, which is the SST, it will come back to the primary tank. Yeah, so this is what I mean by recirculation. So the advantages of employing the trickling filters is very efficient, yeah, for the removal of BOD and ammonia. Just now RBC is ammonia, nitrogen and nitrogen kan. So use a minimal amount of power. Yeah. Disadvantages: power breakdown, yeah, cause gravel bed dry, bacteria died and smelly condition. So these are the major disadvantages lah, of employing the trickling filters. Yeah. Apart from monitoring, yeah, the colors of the slime, we can also monitor the pH, the concentration of the waste, the concentration of the oxygen. Yes, because these are the common parameters to be monitored. Yeah, whenever you run a biological system. Okay. So the expected pH is around 7 for BOD removal condition. For ammonia, sometimes the pH is higher, about 8. Yeah? So that's why whenever you have high concentration of protein in your sample, definitely you will get higher pH. Yeah? Because whenever a higher protein concentration can cause higher ammonia production, thus increase the pH value. Okay, recirculation. Okay, recirculation in a trickling filters is a system where we recirculate the effluent. Okay, we have to recirculate the effluent for what? To reduce the organic loading, to improve the sloughing, to reduce the odors, and to reduce or eliminate filter by a bonding problem. Okay, so we would like to promote more activities. That's why we employ recirculation in a trickling filter system. On top of that, yeah, because trickling filters normally exist as a one single unit. It's not in a series of the train or drum like RBC. That's why it's good to apply a recirculation. Yeah. Uh, so we need to. So in this example, we have two examples. First, to calculate the total flow. Second, to calculate the organic loading. You have calculate. I have shared with you just now on the example of organic loading. Now let's see the total flow. Yeah, there are two examples here. First, I would like to share with you how recirculation rate can influence the total flow. Yeah, for example, the formula below can be used. Inflow times recirculation rate plus 1. Yeah, so case 1, yeah, the trickling filter is currently operating with a recirculation rate of 1.5. Yeah, so calculate the total flow. You calculate the total flow whenever the influent is equal to 4.25 megagallon per day. In second case, The inflow flow is 72 mgd, but the recirculation is only 0.009. I would like you to see the difference, to compare in terms of the answer. You can see here, when you solve for this equation for the case 1, to calculate for the total flow, the recirculation is 1.5. Yeah, you can see the actual flow is 4.25. When you employ recirculation, the total flow will become 10.63. But in case 2, the total flow is 72 mgd. But since the recirculation is very small, there is not much different, from the original flow to the total flow. So these are the major difference whenever we employ the recirculation. Okay, so I think that's all. Not yet for today, but we still have the MBBR. Okay, let's watch a short video on the MBBR. So after this, we can continue with the calculation on how to design the system.
The ideal MBBR is a state-of-the-art fixed film biological process used in municipal and industrial wastewater treatment for BOD and COD removal, as well as nitrification and denitrification. One concept of applying the moving bed biofilm reactor, or MBBR process, is for industrial pretreatment, which shaves off 60 to 80% of the influent BOD, all while lowering the loads heading to publicly owned treatment works, or POTWs. The MBBR process is a 100% flow-through process, meaning the flow rate of the reactor effluent is the same as the influent coming into the reactor. In industrial applications, the water level, or side water depth, is maintained by the gooseneck effluent piping on the outside of the tank. This allows for the reactor to reach its maximum retention time, and for complete submergence of the media retention screen. The inside of a reactor does not have moving parts that will require maintenance. First and foremost, each reactor will have specially designed, submerged, freely moving biomedia, providing abundant surface for bacteria, or biofilm, to grow and thrive. Bacteria will grow on the media in multiple layers, allowing the MBBR to be very robust and self-regulating. If an event were to occur, such as a giant pH swing, the media will not lose all of the layers of the bacteria, giving the MBBR the opportunity to recover much quicker than other processes. The bacteria digests the organics in the waste stream and converts the soluble material into biomass, which will be removed downstream by a solid separation system. An MBBR for BOD and/or COD removal or nitrification is an aerobic system, meaning oxygen is introduced into the reactor to allow bacteria growth. Oxygen is brought into the tank by having blowers send air through stainless steel aeration manifolds. The aeration manifolds are strategically placed inside the tank to have even coverage throughout the entire volume of the reactor, and to provide the necessary mixing for maximum treatment during the reactor's retention time. Stainless steel media retention screens are placed on the effluent flange, as well as the overflow and drain flange, to prevent the media from escaping the reactor. The continuous movement created by the media in the tank scours the screen and minimizes any deposition of solids which could create any head loss. Even though the MBBR is robust and can handle many load variations, there can be times, especially in industrial applications, where additional nutrients will need to be supplied. In those cases, an ammonia or phosphorus source may be needed to maintain the proper ratio for the bacteria to thrive and remove the desired amount of soluble organics. Anti-foam may also be needed if the waste stream tends to produce foam. The World Waterworks ideal MBBR process provides the smallest footprint biological system. For industrial clients, World Waterworks specializes in cost-effective pre-treatment systems, such as combining the MBBR with its own ideal DAP system. The design is simple to operate, at a low capital cost, all while staying tolerant of both load swings and temporary load deprivation. We at World Waterworks are ensuring our wastewater treatment systems meet today's challenges while preparing for tomorrow's needs.
Okay. So these are the moving bed bioreactor system. Yeah, moving bed bioreactor system, where a system. This is
Alhamdulillah.
okay. So the moving bed bioreactor system is more or less a system like RBC and treatment filters. The only difference is the filter media uh, are moving, yeah, within the tank. Yeah, the filter media in the RBC as well as the trickling filters, they stay within one place, not moving. But in the moving bed bioreactor, the filter media, they are swimming, yeah, within the in the water tank. They are moving, yeah, they are moving. So that in some cases, yeah, it can have a better removal. Why? Because the movement of the filter media within the tank can improve the a better contact, yeah, between the microbes, the food, the waste, as well as the oxygen. And again, the MBBR system is an aerobic system. Okay.
Saya duduk. RM200. Saya dah close position long saya.
It is now 8:03. Talk about daily load and loading rate. We're talking about BOD. So how much?
Okay. That is my start. Okay. All right. Okay. We can watch another video. Oh, the video is no longer available. Okay, the video is no longer available. Okay. Alright, then we shall continue with the MBBR system. Okay, so basically these are the process of a fixed film process of an attached growth process, where the filter media is floating and free moving, free to move within the tank. Okay, so these are the actual photo of the media. Yeah, let's say we have this. They are made of plastic. Yeah, the diameter of this media is about 1 centimeter. Yeah, very small. Okay, so these are the photo of the filter media after few months of operation. Yeah, you can see the microbes get intact with the media. Yeah, so that they stay within the media. Yeah, so this is what do we want. This is what do we call as biofilm. Yeah, layer of biofilm, the proof, yeah, of having the microorganism within the media. So we provide a house, yeah, we provide a good space, a small space for the microbes so that they will feel secure, yeah, to stay, yeah, within the media. Okay, so this is actually the spirit of having the filtration filter system, but employing the MBBR will promote more contact. Yeah, it will promote more contact between water, the wastewater, as well as the microbes and also the oxygen. Okay. So these are the actual flow, the actual diagram of the MBBR. Still, we have to use the screening process, the grid removal process. Yeah? But employing this system, yeah, we are going to we can combine the aeration tank, the aeration tank with the primary tank, and this is the secondary clarifier. Okay, we'll need a sludge treatment. Okay, so how does the system works? The pieces of the biofilm will provide a better solution, for the removing waste in the water. So currently we do have one in Langkawi Island, but that one is operated still under pilot scale lah. But they are moving forward to use this system for the treatment of domestic wastewater. But soon they are going to use for the treatment of food and beverage industry wastewater. Yeah. So the the advantages of this system is a perfect wastewater solution for space constraint, easy to use for inexperienced plant operators, require requires require little maintenance and resistant to shock load. Yeah. So this one is more robust. Yeah. The system is more robust because they are resistant to shock load. Yeah. This is due to high population of microorganisms within the media and the better surface area. Alright. Okay. So we have one more calculation. We have two more calculations to cover today. Okay. All right. This also the uh, these are also the revision. Yeah, we have covered this in during in environmental engineering subject. But the reason why I included here because you need to use this calculation in your project. Okay. All right. Compare the area requirement for conventional trickling filters with loading of 0.1 kg BOD per meter cube day and conventional activated sludge with loading of 0.56 BOD per meter cube day. Okay. So in this case, we are comparing the area required based on different loading rate. Yeah. So in this question, you need to design for the triggering filters as well as you need to find the area required for the trickling filters as well as the area required for the aeration tank in the conventional activated sludge process. Okay. So you are given the information. First is the information on the loading rate, which is 0.1 for the trickling filters and 0.56 for the for the aeration process. And you are also being given the concentration of the BOD and also the population as well as the average flow of the wastewater LPD. Is uh, liter per person per day, or sometimes can also be written as L per LCD, liter per capita per day. So these are the amount of the wastewater produced, average flow average flow of the wastewater produced per person per day. In this question, these values are given 200. If it is not given, then you can take as 2 to 5. I repeat, in this question, this value is given. So you have to use this value. Unless otherwise stated, then you have to use the value of 2 to 5. Okay. Take filter depth and area of the aeration tank is 2 meters and 3 meters for the, take filter depth. This is the filter depth. This is the depth for the trickling filters, which is 2 meters, and 3 meters is the depth for the aeration tank. Okay. And then after you have complete this, after you have calculated the area required, then you consider the area required if the primary tank has removed 30% of the BOD. Okay. All right. First, how to solve this question? you have to calculate the flow rate. How to calculate the flow rate? You are given the population as well as the average flow, just times lah. So you will get about this value. Then you calculate the BOD mass. BOD mass is equal to BOD times Q. So BOD concentration is given as 250 milligram per liter times Q calculated earlier. So you will get BOD mass equal to 1,500 kg per day. Okay, this is for the trickling filters. Then you can calculate for the volume. BOD mass is given as 15 kg per day. BOD loading is given in the question. So that you will get the volume. The volume is 15,000 meter cube. So these are the volume. To get the area, then volume equal to A times D. D is given as 2. So the volume, the area required for a trickling filters is 7,500 meters squared. Okay, next, compare to the aeration tank. And this is only the aeration tank. Logically, the activated sludge system will require larger area as compared to the trickling filters. But now we are only comparing the heart of the process, which is the aeration tank and the trickling filters. Okay, volume. The same steps actually, since we have the same BOD mass, but you need to change the BOD load, because the BOD load given for the aeration tank is 0.56 kg per meters cube day. So you will get the volume about 2,680. You can calculate for the area, and the area is 893. 893 area required for the aeration tank. Okay. Next question is mentioned that if the primary tanks remove 35% of the BOD, then what happened? Okay, then what happened if 35%? Logically, in any of the system, there should be a primary and preliminary process. It cannot suddenly the biological process. It's almost impossible. Why? Because the system will be overloaded. So in this case, we are considering 35% of the BOD has been removed during primary and also preliminary process. So what to do if you are to consider this removal rate? So again, the information given to you is 35% BOD removed. So 100 minus 35 is equal to 65%. So this is going to be the applied BOD. So the applied BOD 65 over 100 times the concentration of the actual BOD, which is given in the question. So you will get 162.5. These are the concentration of the BOD to be treated, to be used in the following equation in order to calculate for the area. So in the previous example, we use 6 times 10 to the power of 6 liter per day times 250. So in this case, since we have considered the BOD removal, so that of 35%, so that we have to use the new BOD. Okay, then the steps are more or less the same. You can get the BOD mass. So BOD mass divided by the BOD loading. So you will get about 9750. So in this case, in this example, I have only solved for the trickling filters. Basically, the area required is about 4875. Comparing with the system without comparing with the system without any removal during primary stage is about 7,500 meter squared. But in this case, after we have considered the removal rate, the size, the area required is only 4,875 meters squared. Okay. Alright. So these are the examples. Do you have any question for this calculation? Any questions?
No, doctor.
Okay, great. So you need this is already covered in the previous years, but you need to use this calculation later to complete your project. You have only one project, yeah, for this course. I will pass you the project after the test one. Okay, next is on the calculation to calculate for the design, yeah, for the trickling filters as well as the RBC. Um, Okay, these are trickling filter loading. Yeah, a 10 meters diameter single stage trickling filters contains conventional cross flow plastic packing at a depth of 6.1 meters. Okay, this example is not too long. The solution is not too long, but the problem is you have to refer to few tables, before you can complete. You can before you can solve this equation. Okay, before you can solve this equation, you have to refer to few tables. But the solution, the step is not many lah. Yeah. Okay, you can read the question first. Okay, yeah, a 10-meter diameter single stack trickling filters. Yeah, the depth is about 6.1 meters. The primary effluent, with a characteristic given below is applied to the filter. Yeah, so calculate the volumetric BOD and total nitrogen loading. Yeah, I remove K because TKN is total held down nitrogen. Yeah, some people they use TKN, yeah, but I prefer to use as total nitrogen, because to calculate total nitrogen we use TKN. We use TKN. Yeah. First calculate what is the volumetric BOD and total nitrogen loading. Then what is the specific total nitrogen loading. Then what is approximate BOD removal efficiency at 20%, and identify whether nitrification can be expected or not. Okay, why? Because in the trickling filters, we have to monitor this. Yeah, we have to monitor the nitrification based on the nitrogen concentration as well as the BOD. Okay, you are given in this table the characteristic of the wastewater. Yeah, the flow rate is 4,000. The BOD is 1,200. The TSS is 80%. The total nitrogen is 25%. Yeah, all of them are in the unit of gram per meter cube, which is also milligram per liter, except the flow rate. Okay, first, determine the volume, of the trickling filter packing material. Yeah, volume is equal to A times D. Everyone know this. So A is since this is you have to use the formula for circle to calculate for the area. So D is 10 meter squared is given in the question. Divided by 4 is the part of the equation, so you get area equal to 78.5 meters squared. Yeah, so that the volume 78 times 6.1. Yeah, 6.1 is given lah. Yeah. Okay, 6.1 is given. Yeah, so now you can get the volume. Yeah, next step is to calculate the BOD loading. Yeah, to calculate the BOD loading, yeah, is equal to QS naught over V. Okay, you need to calculate for BOD loading as well as the total nitrogen loading. Okay, so for the BOD loading, Q is equal to 4,000 is given. 1,120 is given in the question. The S naught. And what is S naught? S naught is the BOD. Okay, already mentioned just now. The BOD can also sometimes known as the sometimes can also be represented by the S naught. Yeah, and 1 kg. This is only the unit conversion. Yeah, unit conversion. and 479 meter cube is the volume. You solve for this equation, you will get 1 kg per meter cube day. Yeah. Next, you have to determine the total nitrogen loading. Yeah, right. Total nitrogen loading rate, you still use more or less the same formula, but you have to change the S note. Yeah. So in this case, just now, when you calculate for the BOD, you use 120. So now, whenever you calculate for the nitrogen, then you have to use 25. Okay, you have to use 25. So here is 25. Yeah? So that this is unit conversion. So you get 0.21. Okay. Next, you have to estimate the approximate BOD removal efficiency. Okay. Number 4, you have to refer to figure 9.8. Okay, figure 9.8. Let me find the figure for you. Appendix for triggers. Okay. 9.8, which is figure 9.8. Okay, here. Okay, to identify the BOD removal, you have to refer to this table. Okay, can we go back to our example just now? Please have an example. Okay, from figure 9.8, at a loading of 1.0. Okay, since you are to find the BOD removal efficiency, definitely you have to check the BOD loading. So in this case, our BOD loading is 1.0 kg BOD per meter cube day, and from this value, from BOD loading value, you can check the removal efficiency. Any question? Any question? I think someone raised their hand. Shafika? Alright. Okay, so BOD loading in this case is equal to, let me change the colors. Okay, in this case, the BOD loading is equal to 1. Okay, so you draw a vertical line and draw a horizontal line, yeah, so that you will get the BOD efficiency. In this case, BOD removal, sorry, not BOD efficiency, BOD removal, the percentage of BOD removal is around 82%. Okay, that is how we find the BOD removal efficiency. So you have to calculate BOD loading. You have to make sure that you calculate, you have got a correct value. The wrong value of the BOD loading will give you the wrong value for the question number 4, which is the BOD removal efficiency. Okay. Question number 5, can nitrification be expected? Okay, how do we know nitrification can be expected or not? First of all, you need to know what is nitrification. Nitrification is the process of the conversion of the organic matter into nitrate. So this is the process of adding nitrogen into water or wastewater bodies. Okay, so if the process nitrification keeps continue occurring, so that will end up having higher concentration of nitrogen. So normally, whenever nitrification occurs, it has to be completed with other process, which is known as denitrification. Denitrification is the process of the removal of nitrogen from nitrate to nitrogen gas. Yeah? So we shall discuss this in detail after the semester break. Yeah? What is nitrification and denitrification. Okay, so let's see here whether from this condition whether nitrification can be expected or not. Yeah? The answer is no. But how do we know whether it's no, yes or no? Yeah, so this can only be determined from the value. Well, definitely it has to be determined from the value. Okay, let's see. You have to refer to table 9.5. Yeah, refer to table 9.5. Let's see together 9.5 here. Okay, so in this table, Okay, in this table, we are to design, we are to check for the combined BOD removal and nitrification. We have to check for the combined BOD removal and denitrification. In this case, the BOD loading that you have calculated earlier is 1.0 and the total nitrogen is about 0.21. Okay, and you go back to the table. Okay, the table that you have to refer is this one. I put in green here. I hope that you can see my green line here. Yeah. Okay, in this case, what is the BOD concentration just now? In our case, our BOD is 1 kg, right? Yeah, 1 kg. What is the value for the TN? Our TN is 0.21. Yeah, 0.21. So does 1 kg falls within this range? No, because the range that stated here to prove whether nitrification will occur or not, it has to be between 0.1 to 0.3. Yeah. And while for nitrogen, the value is 0.21. It does falls within this value. Nevertheless, since one of them does not fall within this value, therefore nitrification cannot be expected. Yeah, unless your COD is 0.2, your nitrogen is 0.21. So since both falls within this range, so nitrification can be expected. Okay, it has to be both parameters. It cannot be only one. Okay, any question? Any question? Tak? You understand what I mean? Do you have any question or you want me to repeat? You want me to repeat? No. Okay. Faham ke?
Boleh repeat.
Okay. Since we have calculated the BOD loading is 1 kg meter cube day and you have calculated earlier the total nitrogen is 0.21. Question number 5, it asks you to check whether nitrification can be expected or not. To check whether nitrification can be expected, we have to refer to table 9.5. It's given in the appendix here. Table 9.5. So which row that we need to check? Definitely the row of combined BOD and nitrification. Because we have calculated for both nitrogen as well as the BOD. So in this case, I put in a green box here. You have to check whether the BOD loading that you have calculated falls within the suggested value or not, and also the total nitrogen loading falls within the suggested value or not. First, we check for the BOD loading. Your BOD loading is equal to 1.0. So the suggested range where nitrification can occur is 0.1 to 0.3, while your value is equal to 1. So that's why it doesn't fall within this range. What does range of what? A range of 0.1 to 0.3. So then checks for total nitrogen. Total nitrogen, the value that you calculated is 0.21. So and it does falls within this value. Sebab yang atas ni, the top one is BOD, the bottom one is for nitrification, for total nitrogen. So even only one of them does not falls within the range, therefore nitrification cannot be expected. Nitrification can be expected if both of the parameters falls within the recommended range. Okay, faham tak?
Faham, understood.
Okay, great. Okay, next. Even though the total nitrogen loading is appropriate, so at the higher BOD loading, the heterotrophic bacteria outcompete the nitrifying bacteria for site on the packing surface. So this is due to the carbon to nitrogen ratio. Yeah. So in this condition, the concentration of carbon is too high, as compared to the nitrogen. For that reason, nitrification cannot be expected. Yeah, you can see the difference in terms of the concentration. While we have BOD represented the carbon is about 1, and nitrogen represented total nitrogen represented the nitrogen. So if we are to compare between carbon to nitrogen ratio, it's clearly, even before we check the table, we know that this is at this ratio, nitrification cannot be expected, because the BOD is too high, as compared to the total nitrogen. Yeah. Okay, number 6, what is the specific total nitrogen loading? Yeah, so in this case, you have to refer to table 9.2. Yeah, where is table 9.2? Table 9.2 is here. Okay, table 9.2 is here. Let's choose pink in color. Yeah. So pink 9.2. Yeah, this is on physical properties of trickling filter media. Okay, let's study one by one. First, the first column. The first column is actually the packing material that we would like to use. Yeah, the filter media that we would like to use. In this case, is clearly mentioned in the question that conventional cross-flow plastic packing. So these are the keywords, these are the keywords that tell us which row that we would like to refer in this figure. Yeah. So in this case, we are to refer the plastic conventional. Why? Because it's mentioned here, plastic packing. Okay, conventional cross-flow plastic packing. Yeah. So you jangan pergi ambil high specific surface area ke, random packing ke, unless sometimes and this question is easy because the keywords is clearly stated. The keyword is clearly stated in the question. However, to some cases, maybe the keywords is not given. You are to determine which packing material are to be used. Yeah, you are to determine which packing material are to be used based on the characteristic of the wastewater. For example, for example, if the wastewater contain high concentration of metals, high alkaline material, so maybe plastic is not suitable. Why? Because they can be affected by the corrosion. So that maybe you have to use the river rock. You have to choose the river rock. So these are the justification. Sometimes justification is required for you to decide which packing material to be used. Okay, so plastic random packing for high specific surface area. In this case, for high specific surface area, the last row, high specific surface area is good if we have very high concentration, if we are to treat high concentration of effluent, because at extreme concentration, is really required high specific surface area so that we can have more microorganism. Yeah. Okay, let's complete our example here. Number 6 just now. Okay. The specific surface area of the packing is 90 meter squared per meter cube. Why do I get 90 meter squared per meter cube? So in this case, okay, in this case, since we are to refer to this row, we are to refer to the row of we are going to refer to the row of plastic conventional, so that the approximate specific surface area is 90. Okay, this is where they got 90. Then you substitute into this equation. Total surface area equal to surface area. This is per meter over volume. So you will get the surface area. So this one is the specific surface area in the unit of meter per meter cube. So when you cancel out, this 90 is actually 90 per meter. So that's why you can get meter squared here. Yeah, so specific TKN equal to Q and not over A. So Q is given earlier and not is the original concentration of the nitrogen in wastewater. A is the calculated area. So you will get the specific loading. Okay, so that's all. So this is how that we can calculate the specific loading. Depends on the question. It's not necessarily asking you to measure to calculate for the BOD. We can also ask you to calculate for the TSS. You can see the difference in terms of the if we can check, we can combine the BOD. Yeah, we can ask you to check for the BOD only. For the partial BOD removal or during the secondary treatment. So you have to be very careful reading the question. You have to read the question carefully because there must be some keywords available so that you can decide which row that you have to refer to solve for this question. Yeah. For example, table 9.2 just now. Yeah, table 9.2 just now, you can see the application. Yeah, river rock is suitable if high nitrogen concentrations. River rock large is suitable for nitrogen, carbon and nitrogen. Same goes for plastic conventional. But if you are to consider only the nitrogen, so you can see only these three are to be used, which is river rock small, the plastic high surface area, as well as plastic random high surface area. So you have to see the application so that only you can decide which packing material to be used. So sometimes in the question I can mention high nitrogen only to treat the nitrogen, or I can is good to treat for both carbon and nitrogen. So these are the keywords that to be used. Okay, if the organic matter, then we are referring to carbon. The organic matter, then we are referring to carbon C. If we mention about protein, and so that this is equal to nitrogen. Okay, carbohydrate is also carbon. This is carbon. Organic matter, carbo. It can also exist as the carbohydrate. It can also exist as sugar. So all of these substances will contribute to carbon. However, protein, it will contribute to the nitrogen. Okay, so I think that's all for today. You have any question?
Not at that.
Okay, great. Alright, so I'll see you in 2 weeks' time, inshallah. We will be having another series of lecture. But just to keep my words, the test will be covered only up to this week lecture. Okay, only up to this week. Anything that will be discussed in week 7 is not part of the test. So test 1 only cover lecture 1 until lecture 6. Okay. Don't forget to fill up the attendance. Let me have a screenshot of this session. Okay, if there is no further question, so thank you very much, everyone. After your test, I will pass to you the question for the project. I think you do have works to do, right? You have to complete the assignment, both individual as well as the group works, kan? So please let me know if you need extra time, especially to submit the group works. I can consider you to submit in week 9 instead of week 8 if you don't have enough time to submit in week 8, so that I can allow for the extension till week 9. Okay. With that, I thank you. Eid Mubarak and have a pleasant afternoon, everyone. Bye.
Thank you,
Thank you.
Doctor.
Right,
Selamat Hari
bye.
Raya.
Okay, enjoy your holiday. Bye.